Okay, number 61. We want to know, so a charged particle enters a magnetic field region and undergoes circular motion in that region. We want to know, so if its charge to mass ratio is doubled but the velocity stays the same, how will this distance change? So we want to know how the radius of this circle depends on the those parameters. So the way to do this, the way I thought about it is I had the centripetal force, the net force acting on the charged particles as it enters right here is just the magnetic force, QVB, and this thing is moving in uniform circular motion, and so we can set it equal to the centripetal force, mv squared over r. So solving for the radius of orbit, we get mv over qb, where q is the magnitude of this charge. So it looks like it's the same magnetic field. We're going to throw in another particle of the same speed, but we're going to double the charge to mass ratio, so double q over m, which means m over q is going to be halved. So this radius is going to half, and so the distance here is going to half as well. So answer choice E. 62. This is Gauss's law. I'm very explicitly talking about the electric flux through a closed Gaussian surface. So Gauss's law says that now Gauss's law is a statement about electric flux through a closed surface, and you can explicitly write what that is in terms of an integral, but that's not needed here. Here we just need to know that the total electric flux through this closed surface, which is equal to this, the enclosed charge over epsilon naught in SI units. So they tell us that they give us the net charge inside the closed surface. So I can go ahead and plug in 1 times 10 to the minus 9 coulombs here. So I was a little sloppy here. I left out the coulombs and I left out SI units here, but I have in mind that this is SI units for the electric flux. So I did have to remember that this was 8.85 times 10 to the minus 12. I rounded that to 9. 10 to the minus 9 over 10 to the minus 12 is 10 to the positive 3. So 1/9 times 1,000 is about 100. I probably didn't need to keep that many significant figures. So that's the total flux. Now what they've done in this problem is they've selected a patch of the closed cylindrical closed Gaussian surface. And they say that the flux through here is negative 100 Newton meter squared coulomb, which is SI units. So the flux through here plus the flux through the rest of it. So in other words, the total electric flux, which this is the total amount. The total amount is the flux through the patch plus the rest. So this positive, there's a positive net charge in here. So positive 100 is the total. The patch is negative 100 plus the rest. So that means the flux through the rest of this, moving the 100 over, is about 200 Newton meters squared per coulomb. 63. This nuclear decay, as soon as you see a neutrino involved, that is the indication of the weak interaction. So this is definitely D. The neutrino doesn't interact via any other force. Well, that's not true. They have a tiny bit of mass, so maybe a little bit of gravity. But this is definitely weak interaction. That's just something to keep in mind. Okay, 64. An atom has total angular momentum given by... Total angular momentum given by this formula. Square root of L times L plus 1. H bar. Now remember, the total orbital angular momentum is quantized, where L equals 0 corresponds to S orbitals, L equals 1 corresponds to P orbitals, etc. So it looks like they give us the value square root of 2H bar. So if you look at this formula and you look at this, you realize, oh, this is L equals the quantized L. That's L equals 1, which corresponds to a P orbital. So this is a P orbital. So for P orbitals, there are, for a given value of n, there are 3 P orbitals, and those correspond to the 3 possible Z components of angular momentum. So that's the total orbital angular momentum, and then the z component can be anywhere from minus L to L times h bar. So minus h bar, 0, and h bar. Okay, 65. Quantum harmonic oscillator. Spectrum of evenly spaced energy states. Yeah, the total energy can be 1/2 h bar omega, 3/2 h bar omega, 5/2 h bar omega, etc. And the spacing between all these is h bar. Potential energy function is linear in the position coordinate. That is not true. It is quadratic in the position coordinate. So the potential energy function here is 1/2 m omega squared x squared, or 1/2 kx squared. Ground state that is characterized by 0 kinetic energy. No, this is the total energy, and from the virial theorem, you know that on average, that's so half of this is kinetic energy and half of it is potential energy. So I guess the best thing to say is that the kinetic energy, the time average kinetic energy, is about 1/4 h bar omega, but that's kind of fuzzy when it comes to quantum anyway. It's definitely not 0 though. Number 4, a non-zero probability of finding the oscillator outside the classical turning points. Yeah, so even for the ground state, so the ground state of the harmonic oscillator is a Gaussian, and so that's non-zero even outside the classical turning points. So it's a common problem in a first quantum mechanics class to calculate what that probability is. But yeah, it's a non-zero probability. So it looks like 1 and 4 are true. Number 66. So again, this goes back to the energy level of a hydrogen-like atom. So in replacing the electron with the muon, so this goes back to question 50, and it looks like from the answer choices that these energies are proportional to mass rather than mass squared. If it was proportional to mass squared, it would be, there's no reason to have one of the masses replaced with reduced mass and one of them not. Another thing is I know that, so because it looks like we want to involve the mass of the proton, we're not just going to deal with the mass of the electron and the mass of the muon, but the reduced mass of these two quantities. So the reduced mass, so if you have M1 and M2, the reduced mass for a two-body system is M1 times M2 over M1 plus M2. So one of these is going to be a proton for either one of these two atoms, and then there's a reduced mass for the electron and a reduced mass for the muon. So thinking back on question 50, we know that this energy is proportional to mass here. And so it looks like the answer is going to look like this. We definitely know that there's still going to be the 1 over n squared dependence. We still have this minus 13.6 approximately eV. And then this is, so this is almost it, but the answer is going to be the reduced mass of the muon over the reduced mass of the electron. So in other words, E naught is proportional to the reduced mass of the electron. So we need to get rid of that factor and replace it with mu, the reduced mass of the muon. And so plugging in these fractions into this right here, so we don't want this, but we want this. So it looks like the mass of the proton, so when we do this divided by this, one of these MPs goes away. And then we have a mu plus MP on the top. And then this on the bottom, and then, yeah, looks like the rest of it is, oh, no. I even have this circle right here. The mu is on top, so mu plus MP is on the bottom, yeah. Almost got it wrong despite getting it right. All right. 67. A large parallel plate capacitor consists of 2 square plates that measure 0.5 meter on each side. A charging current of 9 amps is applied to the capacitor. Okay, rate of change of the electric field. So we want to know something about the electric field, and I'm guessing we're going to take the derivative with respect to time. But we automatically know the electric field in between capacitor plates. So it's sigma over epsilon naught. It's sigma over 2 epsilon naught for each sheet, and they're adding together in the region in between the parallel plate capacitor. And this is the surface charge density, so charge per unit area. Okay, so this is the electric field in between, and then we want to take a time derivative here, just because that's what we want to solve for here. We want the time rate of change of the electric field. So in looking at this, we need to figure out which one of these is changing with respect to time, and we're told the current. So that means the charge of the capacitor is changing here, whereas the area of the plates is constant. So this it's the Q that's changing over time, so we can take this, these are constants. dQ dt is the current, 9 amps. So right here, I'm just assuming SI units, and then I know that this is going to be, I'm going to be left with SI units. So electric field is volts per meter, and then per second. So I just kind of being sloppy here, and then but being okay with the units out here. This current is 9. This is 9 times 10 to the minus 12, as we saw in a couple problems ago. And the area is 0.5 squared. So it looks like 1/2 squared is 1/4, 4 on the top. So 4 times 9, and then the 9's cancel out. So 4 on the top, and then 10 to the minus 12, when you put it on top, is 10 to the plus 12. And that looks perfect. Okay, number 68. There's some symmetry to this problem. So first of all, there's no reason that so when you hook up a battery like this, the current's going to go this way. It's going to start spreading out here, and it looks like there's no difference between the left side and the right hand side. So it would be really weird. There's no reason to expect that current would be going to the right over here and to the right over here, or left and left. At most, maybe there's like a current going this way for this resistor, and then this way on this one, and then down here, down here, down here. Or maybe in and in. So I'm going to convince you that there is no current right there. So sort of without loss of generality, just assume it's going this way. So if this is the case, if the current is actually going to go this way, then that means that the current through here is going to be less than the current through this resistor. So see how there's current down here, some of it's branching off this way and this way. That means there's less overall right here. So this current is bigger, and because the resistances are equal, that means this voltage is bigger than this one. Okay. But so suppose you were to take the battery and flip it. So instead of this, you had this. In that case, the current should be, so you reverse the direction of the current. It should be the case that there's a bigger voltage across here. So from here to here. So just like before, the bigger voltage was across here, the first resistor we saw in this middle branch, should be a bigger voltage across here than right here. That means that this current is bigger than this one, and so this current is going to go this way and then this way. But that's a contradiction, because if you flip the battery, then all the voltages should change. So instead of currents going this way, they should be going in. So we sort of run into a contradiction there, and so you can expect that, for this reason, there's actually no current going through here. So in other words, we can just treat these as an open circuit right there. And then it becomes very easy. Then you have, if this were just an open circuit, same, no current there, no current there, then these two resistors are in series, these two are in series, these two are in series. So you have 2R, 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 all in parallel, which means that the equivalent resistance is 1/3 of that, 1/3 of 2R. Then you just have a single resistor with that voltage, and you can solve for the current, V equals IR, using that equivalent resistance. Just move this to the other side and you get D. Okay, 69. For this one, okay, so we want the output voltage as a function of frequency. And these functions look very different. So the limiting behavior is sort of an easy way to go about narrowing down answer choices. So first of all, so capacitor acts very differently if omega is infinitely big versus omega being close to 0. So first let's consider omega being infinitely big. If we're looking across the capacitor, so it's true that the voltage across the capacitor, I'm looking at RMS values for this, so not as a function of time. So the RMS value of the voltage is the RMS value of the current that's being delivered to the capacitor times its reactance, the reactance of the capacitor. And the reactance of a capacitor kind of like an effective resistance, which is 1 over omega c approaches 0 as omega goes to infinity. So if this approaches 0, this is definitely going to approach 0, for no matter what the current. So the voltage across the capacitor, which is the output voltage, is going to go to 0. So you can already rule out, so you only need to consider answer choices where it goes to 0 as omega goes to infinity. So you can rule those 3 out. So then there's a difference between these two as omega goes to 0. You want to see, does the output voltage, should that equal something or nothing? So in the limit omega goes to 0, this is like a DC circuit in that case. So if you imagine replacing this with just a DC battery, then this thing has all the time in the world to charge up fully. And the voltage here is going to be the same as the input voltage. In other words, the ratio, the gain here is going to be 1 because these two are going to be equal. So we want a function that's 1 for omega equals 0 and dies down to 0 at infinity. So it looks like D will get us there. All right, 70. So they give us information about the area of a loop. It's placed in a magnetic field, and they tell us that the initial magnetic, so this loop of wire is in a magnetic field of this strength, and then we pull it out. So there's going to be a decreasing magnetic flux through the loop, and they didn't tell us the time here. So what I did, I suppose this is cheating somewhat. I said, suppose I pulled this out, pull the wire out in a time delta t, and then just pray that as you go through the algebra, the delta t will cancel out. So the answer shouldn't depend on delta t if they didn't tell us what the time was. So I'm using Faraday's law, assuming delta t and hoping it cancels by the end. So for Faraday's law, the induced EMF, so what I have in mind is minus the change in magnetic flux over time. And then replacing these differentials with finite values, so delta t and delta flux. And for delta flux, it'll be, because the area is some set value, it's going to be the change in magnetic field over that change in time. In the area, I just replace it. This we were given. What did I call it? S squared. That's weird. I could have just left it as A. I don't know why I called it S squared. And it talks about how much charge going through a point in the wire. So what I've done here is, so to get to charge, I got to do a couple steps. I got to say, well, induced voltage is related to induced current, and then induced current is related to charge going through a point. So I assume I have some resistance here to relate this with induced current, and then the current, the current I can relate with charge right here. By saying, well, whatever that induced current is multiplied by the amount of time, and then that's the charge. And it looks like the delta t's do go away. So if I plug this in right here, so this has a 1 over delta t, and then multiply by delta t, those go away. And I have the resistance left, but that's fine because they give us the resistance right here. So as I prayed at the beginning of the problem, the delta t went away. So it looks good. I can plug in the area right there in SI units, so you got to be careful you got to convert that to square meters. So you got to divide by 100 twice. So it's not 0.1, but 0.001, or 10 to the minus 3 for the area. Meter squared. This is the magnetic field in SI units, and then the resistance is in SI units. So 1/10 times that is 10 to the minus 4 coulombs. 71. This is a similar formula to the last time. Magnetic force is equal to the centripetal force. You can solve for the radius here. So we want to get a ratio of two different circles, and what's different about the two other than the radius? Which one of these changes? Well, looks like the speed is the thing that's allowed to be different. It's the same mass, they're both electrons, same charge, same magnetic field. So the ratio of the r's, since r is proportional to v, the ratio of the r's is the ratio of the v's. So r1 over r2 is equal to 1/3. That means this is equal to 1/3. You get the answer B. 72. I got this wrong. So I'm aware of the Pauli exclusion principle, but so I thought that the Pauli exclusion principle was the fact. So if the definition of Pauli exclusion is that fermions have antisymmetric wave functions, then A is true sort of vacuously. bosons obey the Pauli exclusion principle because the Pauli exclusion principle applies to fermions, so it's vacuously true. But I guess that's silly because then if that were the case, then A, D, and E would all be true. So I guess it's kind of silly selecting E. But so I suppose the Pauli exclusion principle only applies to fermions, and it's the statement that they can't have the same quantum numbers. So it doesn't. You wouldn't say that the bosons follow that. I don't know. To me, that's sort of semantics, but I guess it's important. 73. The discovery of the J psi particle. This is a particle physics history question. The J psi is a CC bar meson. And this was the first experimental proof that this fourth quark existed, the charm quark. And it completed that second family of particles. So every now and then there's a question that it just, it's hard to, it's hard to guess, I guess, if it's just a history question. All right, 74. Mirrors. So for this, I drew a ray diagram, actually. I said, well, okay, if this is the center of curvature of the mirror, then that means the focus is halfway. The focal length is half the radius of curvature for a mirror. And this is a diverging mirror. So this principal ray will be reflected so that if you trace it back, it goes through the focus. So this is sort of sloppy, but this should have been through that focus, and then the straight line bouncing back. And then another principal ray it hits the very center of this. So the angle of reflection equal to the angle of incidence. This just bounces right back. And again, tracing it back, it looks like the image is right here. So you get a upright virtual, because light rays don't actually come from here. Upright virtual reduced, because it's not as big as this one, reduced image. So it looks like, so it's definitely to the right of the mirror. And it's not all the way over here. It's about R/3. That's about right. And I plugged in some numbers to see if it's, well, they did say that this was the radius curvature right here. So you can actually be quantitative about it too and make sure that this, so it looks like 2/3, so the image here is 2/3 of the focal length, which looks about right here too. So good. So 2/3 of the focal length means 1/3 of the radius of curvature. 75, thin film interference. If this is soapy water, then that means that this is air. Whoa. Sorry about that. That means this is air, this is water, soapy water, and this is air again. And that's important because at this interface, so we want to compare the light that's reflected off here versus the light that is transmitted here but then reflected off this interface. And if you're in air and reflecting off water, you undergo a phase flip, a 180 degrees phase flip, but then reflecting off here, you don't. So in drawing the wave, I drew it so there was a maximum right here just to keep track of phase and everything here. So I drew a maximum. The reflected wave undergoes a phase flip, so this is the one that bounces right back from the interface. And then the one that's transmitted, so I just sort of guessed a quarter thickness. So I just wanted to see what would happen. So quarter thickness, and this is the wavelength in water, by the way. The wavelength is going to change once you pass from air into water. The wavelength in water, take 1/4 of that and say that the thickness is that. Okay, so if that's the case, this is the phase of the wave. It's going to continue on. So if this wave were to continue, it would be negative right here. So I continued it. So it's going back, and it has negative, not amplitude, but value. And it looks like it's at that negative maximum. So this would be constructive interference. So if you have this thickness, you have constructive interference for the reflected light. It says the film appears dark for long wavelengths and first appears bright for this wavelength. So you can see why at long wavelengths it would appear dark, because if this doesn't have enough time to reflect right here, so you undergo a phase slip right here, but say the thickness was really. So another way of thinking of long wavelengths is small thickness. So if you had a small thickness, then this would transmit. It would undergo no phase slip right there. It would come right back, and then there would be no phase slip. So that'd be destructive interference. So the problem is making sense. First appears bright for this wavelength, so we can get the thickness right here. So this is the first wavelength for which it appears bright, 540 nanometers. Now, we don't know whether this is the wavelength given in air or in water, but let's hold off on that. So I can start to guess what this is going to look like if I look at bigger thicknesses, or sorry, shorter wavelengths. So if I look at this wave, it's going to bounce back and go back this way, and you'll have destructive interference. If the thickness, if you have half wavelength equal to the thickness. But if you have 3/4, it'll do the same constructive interference. So looks like we need to, so the wavelength needs to decrease by a factor of 3 in order for it to get the next constructive interference. So that's why it's the 540 nanometers divided by 3. Now this is either air and air, or the wavelength in water and in water. So I just assumed that they wanted a consistent, whatever they were looking at, wavelength here or in here, they wanted consistent with the answer and the initial value. Okay, number 76. This one had a little bit of algebra. Okay, so we want to know what angles. So we want an inequality for the angles for which the light will stay in the optical fiber. So that means that this alpha needs to be greater than or equal to the critical, and notice how they weren't really picky about greater than or equal to versus greater than, so I just chose greater than. Alpha greater than the critical angle, which is the arc sine of 1 over n. It's air out here, so just n equals 1. Okay, so then it was a little bit of trig. So eventually we'll want to relate n and theta. So we gotta work our way. So this relates n and alpha. So we can relate alpha and beta, and then beta and theta. So alpha is related to beta because they're complementary angles. So beta is 90 degrees minus alpha, and so so I have beta 90 degrees minus alpha. Oh, so if alpha needs to be bigger than the critical angle, then that means 90 degrees minus alpha needs to be less than 90 minus the critical angle. So it's just plugging this into here. And I call this angle gamma. So let's hold off on that. So remember, the point is to go from alpha to beta to theta. So beta we can write in terms of theta by using Snell's law right here at this interface. So n sine beta is equal to n equals 1 times sine of theta. Okay, so for beta here, I can plug in arc sine of sine theta over n. So I plug that in right there. And this is less than gamma. And gamma, which is 90 degrees minus theta critical, gamma, I want to write it as arc sine so that I can just quickly take the sine of both sides of this. So I started off writing this is equal to arc sine of some angle. So sine of gamma, so I make this, so at this point I make this right triangle involving theta critical. So theta critical is defined with this right here. It's the arc sine of 1 over n. So the sine of this angle needs to be 1 over n. So I can draw a 1 and an n right here, which gives me the side length just from the Pythagorean theorem. So this squared plus this squared needs to equal n squared, so that gives me this. So if so 90 minus theta critical is gamma, so that means this one right here is gamma. And I want sine of gamma, or I want gamma equals arc sine of what angle? So sine of gamma gives me the thing that I need to put in the parentheses right here, and sine of gamma is opposite over hypotenuse, so square root of n squared minus 1 over n. So now it's perfect because I can take the sign of both sides, and then this simplifies right away. Now I can get rid of the ends, take the arc sign right here. And then this is exactly, maybe amazingly at this point with all the algebra. I think this is one of the most algebraically intensive problems on the exam. So definitely skip it if it's feeling hopeless. All right, 77. We want to relate temperature, average time between collisions, and m. So an equation that popped into my mind right away relating m and temperature is, again, using equipartition theorem. I know that T is proportional to 1/2 mv squared, or mv squared. All right. So the temperature is fixed. We want to see how this depends on m. So if we were to say double the mass of molecules, but at the same at a given temperature, what happens to the time between collisions? So here I need to sort of translate v in terms of time. And I'm assuming that the faster the molecules go, the shorter the amount of time it's going to take before they collide. It makes sense that time would be proportional to 1/v rather than 1/v squared or 1/v cubed. Just assuming, and now I'm assuming that the intermolecular spacing is constant. So I'm assuming the density is constant. And so I go back and I kind of think about whether that might be okay. So PV equals nRT, T is fixed. Density is moving the V over to the other side. So it looks like, I don't know why I wrote this. This should actually be, they're inversely proportional to each other. But if T is constant, it looks like density and pressure, we don't have to change those. Looks like those can be held constant. So I'm feeling okay with this at this point. Okay, so if time is 1/v, then, so this is fixed. So this is constant. I can take the square root of both sides, take the inverse. Looks like so time is proportional to 1/v. So to get 1/v, I move the v squared over to here, and then take the square root. So it looks like square root of m. Yeah, so it makes sense. You have constant energy per molecule. The bigger the mass, the slower they're moving. So it makes sense that it takes more time for them to collide. Right, so that's one way to see that maybe the answer is not 1/m. The more massive, the less time. That doesn't quite make sense. All right, 78. So this, if you've seen a class, if you've taken a statistical mechanics class, you're familiar with partition functions and the probability that you'll find a particle in a given energy state. So if there's two possible states here, then this is the partition function, the sum of, so this quantity appears over and over again in StatMech, e to the minus energy over kt, or e to the minus beta e. So you sum up this for all the states. There's no degeneracy factors or anything to worry about here. They didn't say anything about any of the states being degenerate, so we have no factors here to worry about. So it's either in this state or in this state, and this is the probability that you'd find the particle in state 1. This is the probability that you find in state 2. So if you add these two, see how you get 1. You're going to find it somewhere. Yeah. 79. So the ideal gas law is PV equals nRT, and n equals 1 mole in this problem. The van der Waals correction does two things. It accounts for the fact that molecules take up space, and on average, normally this A is positive, on average they sort of attract each other. So the actual volume, so this is the ideal volume. The actual volume is bigger than the ideal volume because of this. And the actual pressure is less than the ideal pressure because of normally a constant A, because the intermolecular forces are normally attractive. Anyway, you have this formula, and you want to calculate work in expanding from V1 to V2. So work is integral of P dV, and you can still solve, despite the complications here, you can still move the V minus B over and subtract this and solve for P by itself. So it looks sort of complicated, but really just integrating these two terms isn't so bad. You get a log here, and then integral of 1/v squared is minus 1/v. So you get those two terms here. You get the log, and then the 1/v terms right here. All right. So this problem is testing, it wants you to relate frequency with spring constant with mass. So we have two springs, one of them, so two springs attached in parallel. What that does is effectively increases the spring constant by doubling it. So in other words, if you compress, so if you just had one spring and you compress it amount, it's going to push on this thing with some force. If you have two of them and you compress it that same amount, you're going to have twice the force. So that's the same as having the spring constant, which is in newtons per meter, effectively doubling. So K is doubling by attaching them in parallel like this. If you attach two springs in series, you have this, they add harmonically. So it'd be 1 over K1 plus 1 over K2 equals 1 over K effective. So K is doubling, and you're attaching it to a block that weighs 8 times as much. So you have this equation in mind, you're doubling K, and you're increasing M by a factor of 8. So double here. So overall, this is 1/4 of what it was inside the square root. And taking the 1/4 out, you get 1/2 of the original frequency. So this is angular frequency, but if angular frequency halves, then the overall frequency halves as well. So 1 hertz goes to 1/2 hertz.